Hello everyone, I welcome you to a class today which is very conceptual and very interesting. You'll understand how process moves from one state to the other. In today's class, I will discuss Markov jump chain, how the probabilities work, how these probabilities are related to generator matrix transition intensities, and then we'll solve some problems. Let's get started. If you see the time I've written 1, 2, 3, 4, 5, 6, 7 that way. There is one unit time gap. It was a discrete state stochastic process. I'm more interested in how it moves. You see, 2 to 7, 7 to 8, 8 to 4, 4 to 3. That way it moves. So it can go from any state to any other state. Okay. And now when it comes to a random walk, in a random walk, either you can go one step up or one step down. These are the only two possibilities. In the class, I will discuss Poisson process, Markov jump process, how they are connected. This is very interesting and it will be informative for you as well. Just see, we are operating in continuous time, discrete state. States are discrete anyway, but time is continuous. So let me write 5 here and I will make it a stochastic process. Again, remember when I talk about a Poisson process, that means the time is continuous. I've written only these points so that I can give you a visualization. That is the only reason. Here, this is my 0. Poisson process starts at 0. So let me write 0 here, 0. And then this is 1. One time unit. It could be 1 year, 1 hour, whatever you say. But in continuous time, it operates 2, 3. That way it will continue. So when we say a Poisson process has rate lambda. What is lambda here? I will draw the diagram as well. What will happen is it will start at 0 and then suppose lambda is 5. Next time it will go to, see, if you write states like this 0, 1, 2, 3, 4, 5, I don't have space. Okay. So just accept that 5 is somewhere. 0, 1, 5 is somewhere. Okay. Like this. Suppose this is 5. Here also a 5. And next time it will go to 10. So what will happen is next time it will go to 10, then it will go to 15. This is lambda. So what is the waiting time here? We'll go to that and we'll compare it with a Markov process as well. Surprisingly, they are similar. Now this is my Poisson process. See, it gets increment lambda at a rate of lambda. It's going this way. Okay, that we know already. So I'm going back now. Suppose we are here, again continuous time, and the state is somewhere here. Suppose insurance company has already, suppose 3 claims. From 3, it will move to 4, or next time if you see, next instant, it will be here. There are only 2 chances. So what will happen if you see here in between, 5 claims, that is the rate in 1 day or 1 year, whatever you take. But if you take the next instant, okay, very short time duration, what will happen? Either it will continuously stay here or there will be one increment, okay, 0 and 1 increment. This is what you must have studied in a very small time interval. A Poisson process either stays here or goes to the next state, which is one more than this value. That means if I write a number here, suppose you are at 2 here, next time it will be at 2 or it will go to 3. These are the only two ways. One increment or no increment. 2 to 2, 2 to 3. Ultimately it's 5 after 1 day. That's a separate thing. But I'm not talking about that. So 2 to 2 or 2 to 3. These are the only two options. Poisson process. Before moving state, see, continuously it will stay, then it will move. It's like this. The diagram will be, it will continuously stay, then here it will take a transition. Immediately, very small, it's not discrete time, it's continuous time. So like this. Make a transition to the next state, the interval, the moment actually, okay. Suppose I'm teaching the class now, immediately I will stop. Then I will go to the next state. Now come to Markov jump process. In Markov jump process, what will happen? Suppose at time 2 it's there. From time 2, it can go to any state, not necessarily 3. it can go to 0, it can go to 1, right? It depends how many states are there. It can go down, it can go up, anywhere it can go. That is the difference. Okay, so let me go down here. We'll compare here this way. The rate is lambda. Remember here, Poisson process, if I write rate lambda, suppose I'll write rate lambda here, our Poisson process with rate lambda. Now the diagram is, this is 1, this is 1, this is 1, this is 1, this is 1. So the diagram, if you see in a Poisson process, typically you will see something like this. Typically you will see something like this. From here to here, lambda you will see. You write anything, suppose 0, 1, 2, 3, 4, that way you can write. So what will happen is the rates are written. It's not that these are the probabilities, because what will happen is 0 to 1. Whenever 0 means, suppose an insurance company has no claim by now. Suppose I want to give a class in offline mode. I'm waiting for the students. Nobody has arrived. So my state is 0. From state 0, I will go to state 1. 100% probability that I will go to state 1. There is a 100% probability that from 1 I will go to 2, right? When someone will come. These are not probabilities. These are transition rate is given. Okay, these are rates actually. At a rate of lambda. If lambda is 5, in unit time, it will go, it will jump to 5. Suppose I'm counting every hour, how many students are coming to me. Suppose now 0, after 1 hour 10, after 2 hours 20, after 3 hours 30, that is lambda. Lambda is the rate. That is the transition intensity, the rate, but measured in 1 hour. Okay, you can say instant, but measured in 1 hour. At this time, I am expecting at a rate of 10 per hour. That is lambda. Anyway, the more you think, I mean, we'll apply to a problem today, you will get 100% conceptually. This is very important because the 20 problems you will do, everywhere will use this concept. Okay. So 0 to you can go to 1. There is nothing called 0 to, you can never go to 0 to 2 in Poisson process. So if I say this, you can never go to 0 to 2 in a Poisson process. So let me make it Poisson process rate lambda. So here in this case, only one way is there. You cannot come, I mean, you cannot go 2 step up. Again, from 1 to also you can never come to 0. From 1 also you can never come to 0 because it's only, you see the claims process. Okay. So that's how it works. So again, this is not there. This is the diagram. Okay. This diagram you need to remember. And also not only the diagram, but also the matrix at any number. Suppose I will write 5 here or 3 I will write. From 3, either it will go to 4 or it will remain at 3. That is Poisson process. So 3 to 4, if you see 3 to 4, lambda is written already. And also there is no self-loop diagram. In case of a continuous time process, you have to write minus lambda. Okay. If this is lambda, this will be minus lambda. I explained in the last class. You can go and watch. Others are 0. There is no other way here. And this is generator matrix. Okay. Let me write generator matrix for Poisson process. Able to write one row, you will be able to write all rows. How about 4? Similarly, you write here minus lambda, all are 0. That way you can make the matrix. If you want to write 2, suppose 0, 1, 2, that way I will write. If I write 2 here, for 2 also, you write that way. So we'll complete this. This is my generator matrix for a Poisson process. These are the mu ij's, you can say. Mu ij's, because this is also a part of Markov process. So that way, these are the transition intensities and this is the generator matrix. Okay. Now, if you see here, before moving to the next state, what is the time it occupies at 0? Let me try. It's like this. Suppose you have a process and it stays here for some time. That is called occupancy probability. It will occupy the state. I'm giving you a class now. I'm occupying this. Then what will happen? It will make a transition. This is continuous time and instant transition. Okay, little bit I'm here writing so that you'll be able to follow. This is the transition. Okay. And this transition is what you must have studied in CM1. What is that? Force of mortality. Anyway, that's a separate thing. So this is one state, this is one state, and there will be transition. This is called your occupancy probability. Okay, I'm talking about Poisson process. Suppose this is any value 5, it will continuously stay at 5 state, then it will make a move to, it will make a transition to state 6. Only one increment possible, no decrement, no double increment possible in case of Poisson process. So this is the time, this time is called occupancy probability. So this time it will hold the state. Suppose whatever time I've taken, I've decided to give you today is not decided. That means whatever time I will occupy here, that time is called my occupancy probability in this state. I will occupy this much of time before moving to the next level. Do you know anything about this time? Yes, we know. This time follows an exponential distribution. This is the waiting time, you can say. Different notations we have. We write sometimes 0 to 1, T naught, 1 to 2, T1. That way we write. So anything you write, I'm just writing T here. It doesn't matter. T follows exponential lambda. And what is the average waiting time? The average waiting time is 1 upon lambda. So this is there for Poisson process. So let me draw a line here. This is for Poisson process. However, when you go to general one, the Markov process we are studying now, it will stay at 5, and this is occupancy probability. I mean, this is occupancy of the holding the state, occupancy time, you can say, before transiting to the next. But the next is not 6. It could be anything. That is the problem. See, it can go here, it can go here, it can go here. So the transition could be to, it could be to any state possible. Okay, it could go anywhere. So what will happen in that case? Because you have so many, here, what will happen is you have to decide now from here where it will go, here to here, from here where it will go. Now what will happen? Suppose I'll write the state instead of 6 here, one increment. I will write different names for the states. Okay, it could be, let me write A, B, C, all that. Okay, A, B, C. T is the waiting time here. Here also T is the waiting time, but I have to write now waiting time. We normally use W. When you write waiting time W, W will follow exponential distribution same, parameter same, but now parameter will be lambda I, and this is Wi. So here lambda I was not there, because remember, in the Poisson process, in the base form, we always accepted that the rate is lambda. It's the same. Okay. So what happened is, when you are taking the same, this way there is only one kind of a transition, one increment is there. So this is constant now, but here lambdas will change. Expected waiting time will be equal to 1 upon lambda I in the ith state. This is ith state. So here staying continuously in the ith state. Let me use some other. Suppose you are staying here ith state, from I to I. Then from I it will make a transition. So if from I it will make a transition, I to A, I to B, I to C, what is the time it will occupy? The expected time is 1 upon lambda I. But it follows what? It follows a distribution. It's a future thing. Okay. Exponential distributed means you must be knowing exponentially positively skewed. Less is more, more is less, that kind of a thing. Okay. So the waiting time is less with highest probability. And what is that less, that magnitude? If you want to understand, of course, you can, you can do that estimation part. Wi follows this. Okay. So how to know lambda I? That's what you need to know. So here lambda I is equal to, and also I'll introduce Markov jump chain matrix. Okay, and how it's linked with generator matrix, and how we can utilize this one also. Mu I j, you know from generator matrix, this one, this is not a problem. J is not equal to I, whatever. This is the sum of all other transition intensities, and this is the diagonal. These are off diagonal. Okay, minus mu I. That's where I wrote minus lambda before, right? That one only, nothing more. So this lambda is equal to this. This one will use. That means if you consider a Markov process, you will get this. This is the difference. You remember everywhere this is Poisson process. This is Poisson process. Poisson process. This is Markov process. Now here, every time we have lambda rate, that means when I say t follows exponential lambda, t I also will follow exponential lambda for every I. You are in the ith state or any state, it doesn't matter. Okay. So I've written I5 here. That's a separate thing. 4 or 5, whatever you say, 5 or 6 lambda. Here, this lambda is constant. But here in Markov process, lambda 1, lambda 2, lambda 3, lambda 4, at which state you are. If you are at state 3, then you have a different notation. Lambda 5, lambda 6, lambda 7, lambda 8, that way. And you can see this one. Okay, let's go ahead. Now, Poisson process we are leaving. We'll only concentrate on Markov process. Now we have two choices here. One choice is, you see how it's changing. This is one time point. This is one time point. This is one time point. And this is one time point. Okay. Now what we'll do is, suppose it's a continuous time. That means in between also we have states. So suppose you want to observe after every equal time. Okay. This is what we studied in Markov chain. So you observe after every equal time. Okay. You can do this. This is one way. So these are the times you must have seen before. Okay, so what we studied before is this. Suppose these are the times. This is one time, 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 this is one time. What is the difference? The difference is, suppose we wrote before this way, this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, that way. Okay. So this is the time when, this is the time, I mean, I could have matched this. Okay, no problem. This is a time, this is a time, this is a time when the state is changing. For example, if somebody comes to me and sees whether I have completed the class or not after every 5-minute duration, that means you are operating, though it's a continuous time stochastic process. I'm teaching you continuously. However, I am watched discretely. It's not that if it's a continuous time stochastic process, always you have to use continuous time only. No, you can never do that. Even that's why we have Kolmogorov equations. This is a continuous time stochastic process. I'm giving you classes continuously. But someone comes here and watches me whether I've completed the class or not every 5-minute duration. So that means a continuous time stochastic process is observed discretely. And that's what is the practical application. And if you remember last time also I taught the same thing. So now here, if you come here, in this case, whether you are watching this way after every equal duration and you want to check it discretely, that's what I taught last time. Okay. So how can you change the generator matrix to a probability transition matrix? But now today, so that means what? If we started from here, because we start from 0 normally, so we'll combine it so that there will be no doubt later. The first two, let's combine. Okay, cut. Yeah, this is perfect now. So now what is jump chain actually? Now what will happen? I will say that person, please don't come after 5 minutes. Whenever I will I will change my state. Okay, I will leave the class. I will go and inform you that my class is over. Then you can allow another one to take the class here. So that is when there is a state change. That means what will happen? I will continue to stay here. Okay, that means in the other case, if you watch the discrete way we are observing the state here. If I write state I, j, k, whatever, if you say, I can write state names I can write. It could be I, suppose this is ith state, then here jth state, here kth state. Okay. Now what will happen? Ith state could be anything. Healthy, sickness, all those things you can write. I to I continuously there. Okay. Now here, where it's making a transition, here it's making a transition. Okay. Here it's making a transition from here to here. Then continuously staying here. And remember, this is very, very small. I mean, to demonstrate, I'm saying like this. And here it's making a transition, continuously staying in this state up to this time just before, and then making a transition here. Okay. So now instead of 0, 1, 2, 3, we'll watch where there is a time change. For example, the person I said you, he comes and sees me where I am. So it's always same only, right? I'm teaching the class, I'm giving the class, I'm giving the class, I'm giving the class. This I is constant. Okay. Even this is my occupancy time. But will not watch at 1, 2, 3 and the transition matrix. If you remember, those things will not use. These are the transition matrix probabilities. This is what we used already. Okay, you have a transition matrix. You know the behavior of the stochastic process through the transition matrix and present probabilities. So we'll not go to that now. That's already over many times. Now what we are doing, forget about this totally. You forget about this time. Okay, we'll not worry about this. We'll only see when there is a state change. Those times we'll measure. Okay, so what will happen? Let me delete. These are no more required. Okay, these are no more required. Let me delete everything. These are no more required. Acha. Okay, I can delete all at a time. Done. Now what will happen? Which times I require? I require the times when there is a transition. This one little bit syncing problem is there. So this one will bring here. There is a transition taking place here. Okay. Again, J should be also very close. It looks little bit far. No problem. And when the transition happened, this is also not required. Technically speaking, the transition happened at that point. We can't have two time discrete times. Okay. This is very, very small. Okay. At this time, there is a transition took place. So to J, this is the time only. This whatever time is. Then continuously staying in J. This is the waiting time in J. Waiting time will follow exponential distribution with parameter lambda J, lambda I in the ith state. So what will happen is this could be 0. Okay. This could be whatever you write 10, 15, 20. I mean, we're observing only at this. So what I want to say is probably there was a transition at this is 5. And then the other transition took place at 15 or 18. So you see the difference here. This gap and this gap, they are not the same. So even because I am not watching here equal intervals, why to keep this? These are not equal at all. This is my occupancy probability. So this I will keep. This also I will not keep now. Okay. So in this diagram, we have only this. Okay. So 5 here, 5, 8, 15. That means what? 0, 5, 0, 5, 18. The durations are not the same. So what we'll say is a transition took place, but this is the waiting time, and waiting time, this whatever waiting time, 5. After happened, we know that it's 5. Before that one, when you are forecasting for future, this waiting time, this is called occupancy probability, holding probability in the state I. So that follows, that will follow. You can write, suppose, W, the notation we use W, you can write I follows an exponential distribution with parameter lambda I, exponential distribution with parameter lambda I here. This is the notation. Okay. Ith state means lambda I. And what is the expected waiting time? Expected, this we will use in our problem, today's problem, 1 upon lambda I. What about this? This, it went to J. So J, this is the expected time in the jth state. This is another exponential lambda j What is expected? 1 upon lambda j we'll use today in the problem. Not only that, this is the expected one. What is lambda I? Lambda I is equal to, if you remember, I wrote mu ij divided by minus mu ia. We can write, or all this, whatever possibilities. Because if you don't know this lambda I, how can you find this, right? So just you use this. Mu ij, j is not equal to I. I wrote already, that is minus mu ia. Better you write minus mu ii. That's better. Small one, minus mu ii. So similarly, here you write lambda j minus mu jj. Okay, that way we'll have waiting time. But what is common with Poisson process? The waiting times in Poisson process, they follow exponential distribution. The waiting time in a general Markov process also follows waiting time. The only difference is lambda we took here lambda 1, lambda 2, lambda 3, lambda 4. And why the waiting time is always exponential? It comes from a different property, memberless property. Okay, so I'm not going to that now. So this is what you need to remember. Then what we'll do is, let me write this one. After this, we'll go to the next one. The next one will be this, the problem where I kept. Probably here I will have, yes, this problem we'll do today. Means you need to solve around 15 to 20. So let me write here. Now, how you can apply. Acha, this also requires another one. We'll use anyway. Let me write here along with this. We'll come back to this. Now, if you remember, we had a here only I will explain. Now, if you see this one, we know holding probability, expected holding time, and the distribution also, waiting time distribution, everything we know. Now the thing is, suppose one is at I, okay? Once it leaves the state I, where it will go? That is the first question. And then, if you exactly want to know what is the probability that it will go, see, it's not only holding time. When it's making a transition from here to here, what is the probability that it will go from I to j? That also you have to know. So what is the chance that it will go to j? Because here also there are so many states. Here also there are so many states. Here I have a state this, I have a state this, I have a state this. In fact, everywhere. So here, why not from I to this state? Why not from I to this state? What is the probability that from I, when it leaves I, then it will go j only? What is the probability that when it leaves I, it will go j? So this probability is actually called, you can write Pij's because we have already taken Pij's for, we'll write, these are jump chain probabilities. This is called Markov jump chain. And Markov jump chain, they're different. What is Markov jump chain? Markov jump chain. Markov jump chain means, suppose you are going from I to j here, what is this probability? Okay. So it will exactly like a Markov chain, because again we are measuring whenever there is a change, but there are a couple of differences. Okay. So what is this Pij? Pij. So these Pijs, so if I write, suppose I'll write P11, P12, P13, P21, P22, P23. There are three states. I consider three states: P31, P32, P33. These probabilities, like these are the probabilities. And these probabilities are not for Markov chain. These are Markov jump chain. Markov jump chain. And they are related to generator matrix. This is generator matrix. And here we can write mu11, mu12, mu13, mu21, mu22, mu23, mu31, mu32, mu33. In this problem, I will show you directly because we can spend so much time on theory. Okay. Now, if you multiply these probabilities with lambda i's, for example, suppose you multiply lambda I to the first row, I'm talking about the off diagonal, okay? Lambda I, then that means lambda I p11, that must be equal to mu11. Let me write the general one. Pij multiplied by lambda I, that will be equal to mu ij. That means these pij's will be mu ij divided by lambda I. That means these pij's will be mu ij divided by this lambda I, we know summation mu ij, summation of all mu's, I is not equal to 0. That means what? If you have more chances here, all mu ij's, these are all mu ij's. And this mu ij you find, this mu ij, this one divided by this plus this. That's all. This is what you have. And this will use actually. Okay. So even where you have problems, sometimes you will feel this one to use is easier than this one. Sometimes this one will be easier than this one. It all depends. Anyway, now in this problem, we will apply everything, whatever I discussed now. If I go to this problem, it says this. I have this much space. It says, you know what? A company has a salary structure with only two different levels. On an average, an employee spends 2 years at a level 1 before either moving to the higher level or leaving the company. So I will take this way. 1, higher level is 2, leaving the company is 3. Let me write here. This is 1, this is 1, this is 2, this is 3. Okay. Now remember 1 to 2 possible, but 2 to 3 not possible. 2 to 1 not possible because you will be promoted. There is no demotion kind of a thing given here. And then even directly 1 to 3 also possible, it says. And 2 to 3 also possible. These are the possibilities. Okay. These are the possibilities. These are the 3 states and these are the possibilities. This is not a Poisson process, remember. This is a general Markov process because in Poisson process, you can't go from 1 to 3 directly. It's not possible. Anyway. Now this is a Markov process. Here what will happen is they've written the waiting time. Okay. On an average, an employee spends 2 years at level 1. If you do this way, it's like this. 2 years at level 1. 0. This is 2 if you start from 0. 2 years. Level 1. Because I am not worried about equal duration. I will see only when there is a change. So this is your waiting time, 2 years. Employee spends 2 years at level 1. That means average waiting time is given. 1 by lambda I is given. 1 by lambda 1 I will take 2 years given. These students don't understand actually. Anyway, no problem. So levels are 1, 2, 3 means leaving. 1, 2, 3. Now it makes a transition at this point to 2 or 3. Two options are there. Either it will make a transition to 2, like here, if you see the state diagram to the right, or it will make a transition to state 3 here. Okay, at this point, there are two options. So we have to write 2 ticks. Okay, either this is possible, this 3 is possible, or 3, this one is possible. There are 2 possibilities here. Okay, if you compare this diagram, 1 to 2 possible, 1 to 3 possible. 1 to 2, 2 to 3 possible. Suppose it goes to 2. I mean, we don't know. What is the chance we have to see? Suppose it goes to 2. Okay. Then there will be a average waiting time at 2. I mean, it goes to 3. That's a separate thing. Already over, right? It's all over. Left the company. 3 means left the company. Here, left the company. Here, promotion. Here, this is entry level, starting level, you can say. Okay, this way. So now, what is the waiting time in 2? The waiting time in 2, it's given how many years on an average? This given 2 years level 1, and then 5 years before leaving. Okay, so if he goes to the stage 2, on an average he stays 5 years. Okay, so I'll write lambda 2 is equal to 5 on an average. Okay, but what is the waiting time, holding time? That's a random variable. Okay, that's what I discussed today. That random variable name is W2 actually, and that follows an exponential distribution with parameter lambda 2 and expected average waiting time. And W1 was expected waiting time in state 1. Okay, so this is the scene. And this time, this holding time, we don't know, right? This is what I've written, W1. This is the holding time. And here also, let me introduce a time. This is another time. Okay. So here, it will make a transition from 2 to 3. Either here also there is a possibility, but here there is only one possibility, 2 to 3, 2 to 1, it cannot come. So it's like this, 2 to 3 here. Okay. Now we'll move forward. These are given. Now, if you see, now let me write the jump chain matrix. I will write jump chain matrix. To solve this problem, you have to know the PI, this jump chain matrix. Jump chain matrix probabilities. Okay. From that, we will find generator matrix transition intensities. Then we'll use Kolmogorov's equation, forward, backward, integral identity, forward and backward differential equations. Okay. Once you solve those, you will get the answer. Anyway, let me write here the values. The values are, if I write here, 1, 2, 3, 1, 2, 3 here, 1, 2, 3 here. And these are the values I need to write. Probability given here actually will not do anything. So nobody is demoted and promotion can occur at any time. Okay. Upon leaving level 1, the probability that an employee moves to level 2 is 50%. So they've given here 1 to 2, 1 to 3, 50, 50. 1 to 2, they've given 50%. 1 to 3, they've given 50%. How about 2? Once a person leaves 2, there is 100% probability that the person will go to 3. That's what written here. Yes. So you write that 100%, 2 to 3, 100%, and these are 0, 0. Now from this one, we'll try to find this generator matrix. And these are zeros. I mean, you might ask a question, 0.5 plus 0.5 is equal to 1. 0 plus 0 plus 1 is equal to 1. Why not 0 plus 0 plus 0 is equal to 1? Because when I claim that it will exactly work as a Markov chain, of course, not equal duration, only when there is a transition that takes place. However, this is 0. Okay, that conceptual clarity you can go through and you can get it. I will not spend time on this, but it's 0. Sometimes we use one also when you are estimating. I'm not going to all those things because the observing state concept is there. Anyway, now this is my generator matrix. How can I get my generator matrix? What I will do is I will multiply, as I already mentioned you, mu ij to lambda I. What are lambda i's? Lambda is given 2 here. So I will multiply this 1 by 2 lambda is. Okay, here I will multiply to this row, I will multiply lambda 1. Lambda 1 means that is half. To this row, I will multiply lambda 2. Okay, lambda 2 is 1 upon 5. So you multiply half here. If you multiply half here, you will get 0, 0.25, 0.25. If you multiply 1 by 5 here, lambda 2 is 1 by 5. If you multiply 1 by 5 here, you will get 0, 0.2. That is 1 by 5. And then here 0, 0, 0. Okay. These are applied for off diagonal elements. Diagonal elements again, finally, again you need to do it separately. Diagonal elements you cut and you add because these are the mu ij's. What you can do is you can add all. Suppose this is 0.25, 0.25, 0.5, you write minus 0.5 mu yi is equal to summation mu ij, that formula. So this will be minus 0.20 and this will be 0. This is my generator matrix. Once I get generator matrix, that means I know from any instant to the next instant, even it's not a second or millisecond, it's next instant. Okay, how it will make a transition? Like you can compare with CM1, force of mortality. Okay, mu, that way. So once you get generator matrix, that operates in continuous time. But again, from continuous time, we'll go to Markov chain. Here, Markov jump chain to continuous time. Jump chain is where we only observe when there is a state change. From that, we came to continuous time. From continuous time, we'll go to again equal duration, whatever I already explained you. So to go to that, we need to solve Kolmogorov's differential or integral equation. That is the only way. So we have to form equations. Okay. So we need to get all these values. What we need is now we got our mu ij's. Let me write here mu ij's. These are my mu ij's. 1, 2, 3. 1, 2, 3. Mu 1, 1, mu 1, 2, mu 1, 3. I don't remember what is that. Probably minus 0.25. Minus 0.25 minus 0.5. This was 0, 0, 0. This is minus 0.20. This is 0.20. These are mu ij's. From mu ij's, I'll try to get p ij's. These are p ij's. P ij's means not the jump chain. This is normal chain. Why this is useful? I'll show you the question now. These are P11, P12, P13. But do you need all? That is something we'll check now. What we need actually? Do we need all? If you don't need all, suppose you want to get only one, this one or this one, you can solve this Pij. We'll write ultimately Kolmogorov's equation, right? So what we need, let me go to the question. What we need actually. So they say, all right, generator matrix, all that we have done already. Part 2, the company currently has 1,000 employees. At present, 60% are at level 1, 40% are at level 2. Okay. We wanted to solve this. So what happened here? We try to find the transition matrix here. Then another transition matrix, P. This is one transition matrix. This is one transition matrix. This is one transition matrix. So this transition matrix is P. So once we know this is 60%, this is 40%, this is 0, then what we did is we went on multiplying matrix 5 times. But that 5 times is not required because you can directly get Pij. Here Pij 5 directly you will get. Why directly you will get? You have two options. Because you will get P, if you solve, let me write here, this is so important. If you solve, let me write, if you solve Kolmogorov, differential or integral equation, whatever, okay? I'm writing differential because I didn't teach integral. Differential equations, forward or backward, whatever, you will get Pij T you will get. I mean, see, you don't need to find Pij1, you put T1, then once you get that 1 year, 1 time period matrix, Markov chain matrix, again you find P5, that's not required because directly Markov Kolmogorov equation gives you Pij. Why not use Pij directly? Okay, so you can do that. You do it directly. So what will happen? You have your Pij. So here what we'll do is, I will erase everything. This is not required. This is not required. This is not required. This is not required. Matrix multiplication. These are not required. Just I will solve and I will try to find. I will put t value. Then I'm done. Okay. So what I will do is, and what is that question? They say 60%, 40%. And what is the question? Let me go here. Okay, 1,000 employees will use. At present, 60% are at level 1 and 40% are at level 2 done. Assuming nobody joins the company in the future, determine the distribution of these employees after 5 years. Okay. So after 5 years, you want. That means they say you find after 5 years. Okay. So that means this distribution you have at time 0 and you need to find at time 5. So we'll find Pij 5 here. Distribution means all we want. So that means somebody, I mean, some persons are here. What will happen after 5 years? That's what you need to find. Okay. All right. So if you, sorry, time and again it's disturbing. No problem. So now what we'll do is, here if you see, suppose I'm interested here. Because if I find 2, automatically the third I will get, right? So if I find this one or this one or this one, suppose I will find this one. Okay, I will find this one. Automatically this one will be known. 60%, 60, 40% means what? What is 60% of 1,000? 600 are here. How many are here? 400 are here. Here we have 600. Here we have 400. So what will happen? Once you know this probability, we'll multiply with 1,000 and we'll multiply with 1,000 and we'll subtract from 1,000, we'll automatically get this. Any two you find, you will get the third one. Okay. Now suppose we want to find this. So we'll see how many will come from here. How many will come from here? How many will come from here? I think this is the only way, right? Because yearly we are not checking. You go there, come back, all these things are not required. Kolmogorov equation will directly give you peace of mind. Pij, put t, you get value. That's all. Okay. So we'll go after Pij. Ij means, for example, here, if I write the states here, state names are 1, 2, 3 here. Here states names are 1, 2, 3. So I have to find P115, P115, P115 means anyway, we'll get T, then we'll see. And what we need to find? We need to find P21, then we'll put 5. Then this is 0 anyway, we'll not find. Okay. So we have 60% and 600. If you want, you can multiply, and 400 you can multiply, you will get this value. Similarly to 2, again you have to find. Okay. So how can you find? Shall I spend time on this? I don't know, but yeah, I'm just doing one of these. Second one, you can do it. And you must have the solution as well. So now what we'll do is how to find P11T. P11T, if you want to find, it's very simple, right? Waiting time, holding time. So P11T will be, I'll not make it complicated here. Now we'll try to use one by one. Suppose you want to find P11T, that will be equal to P11 bar T. You check Y, that's up to you. That will be equal to, that is the E integration, right? That formula. E power summation mu ij, all that you can write, minus how many are going out of 1. If you go to the state diagram, you see how many are going out of 1. This is the state diagram. 1 out of 1 means this one is there. This you can say this 1 to 2, this one is there, or this one is also there. Both are there. So out, going out. So these you will get from 1 to 2, 1 to 3 from here, this generator matrix 1 to 2, 0.25, 1 to 3, 0.25, 0.25, 0.25. This is minus 0.5. Why I have written minus here? I don't know. These are minus. This is minus. Okay. 0.25, 0.25 is here. So that way you can write, this is the formula, integration 1 to 1. So I can write mu 1 to 1 3, summation of mu 1 to 1 3. I don't need to integrate because anyway this is constant, not a problem. Okay, this if you find, you will get some value, e power minus probably 0.5 t you will get. Okay, that to directly you will get. Similarly, then put t5, you will get p115. Similarly, if you want to get 2 to t, you directly apply this formula. Can you apply 2 to this formula? Because bar formula is this. Okay, bar means what? That is staying continuously, holding time, occupancy. But if you go back, you can't come once again, then only you can apply that. Okay, here if you check, when you are leaving this state 2, can you come back to 2? No. No. When you are leaving 3, can you come back to 3? No. When you are leaving 1, can you come back to 1? No. Okay, if I write something like this, I'll write this, then things will change. Okay, then what will happen? P11T will not be equal to P12T. Sorry, 11 bar T. That's what you need to know. Because suppose I am teaching now, I will stop teaching. I will start to another class at 2 p.m. If somebody, I mean, sees now I'm teaching, he comes another at 3:15 and still I'm watching, I'm teaching. So that means what? I left the state, I came back. That's not holding time, right? So that way, the problem will be there. But in this example, there is no problem. Will not worry. Let me delete all. This is not there. So easily I can get 3 probabilities. Then I will use Kolmogorov for others. Already P22, P33, all that I will get. Now suppose I want to get P12. Okay. 1, 1, 1 I'm finding. P11 over P21. I want to find P21T. I will write d by dt, that is Kolmogorov equation. So you can write P21T mu 2 to 1 finally, 2 to 1, 1 to 1, plus P23T mu 3 to I want to 1, plus P22T mu 2 1. So these are the possibilities. This is from the differential equation. Then what will happen? Let me erase all. Happen, you need to solve this. So I already gave a class for this, 1 or 2 classes, how to solve this. But yes, If I take this as y, normally I take this as y to make the life easier. But before making that y, now check which are 0. If you see here, mu3, starting from mu3, anything is 0. So this is 0. So this will not contribute. How about this P21T? I mean, anyway, P21T is there, YY will take mu11 value we have. How about P22T? P22, mu21. Mu21 also we have, mu21 is 0 once again. Mu21 0. So, I mean, if this is the case, then it will be dy upon dt will be equal to y mu11. Mu11 is minus 0.5 y. Because I found that mu21 0. Yes, 2 to 1 to it's to 0, right? So you need to solve this equation. It's very easy. You go through my last video, okay? You will be able to do that. And finally, you can find this value, okay? If you any doubt, you can ask in comments. I will definitely respond, okay? This part is over. Now let's go to the next part. Next part is this. Expected time, okay? So this will be, let me write here. Expected time, you get question from this also, to reach state K starting from state I. This one. What is the expected time to reach state K starting from state I? So for this, what we are saying is, suppose you start at time I, what is the expected time it will take? So to go to K, suppose I'm teaching now, what is the expected time when I will be on the dining table? Okay. I will be taking food. Now I'm giving the class. Okay. So of course I will continue to stay here starting from my, I have to complete the class. So this is my occupancy probability, holding the class probability. So let me write, I will continue to stay here, but it's not that when I leave the class, I will directly go to my dining table. No, maybe not. So to go to dining, what will happen is, probably I will do some other task. I will go to the market. I will go to my friend's place, whatever. I mean, I don't know, right? So I can't write like this. If this is state K, so there will be a transition that will take place for sure. Okay. So here what will happen is, I will go suppose to this state. Okay. So I've started from I, and suppose teaching state. When I leave this state, I will make a transition to some other state. But what is the probability that, not probability, we say what is the, yes, what is the probability that I will go to, we'll find the probability because we studied probability today. We'll go to this, okay? When I make a transition, what is the probability that I will go here? From here again, I will start the process once again. So what will happen here? This will be like, this is called recursion. Recursion means what? The same things will repeat. So whatever way we started our problem, okay, you need to handle this problem. Similar problem again came. Okay, so if you see here, again similar problem here. So suppose when I say I want to go from I to I want to go from I to K, I wanted to go from I to K. Okay. Now I'm saying sometimes I will stay in I, then suppose I will make a jump. This is Markov jump chain. If I make a jump to state J, when I leave I, okay, so what will happen? Again, there is no guarantee that directly I will go from J to K. Probably I will stay sometimes in J, then I will make a transition to some other state here. Okay, I will make a transition after staying some time in J. Then what will happen? Then again J to K I have to think. there is no guarantee that J to K directly I will go. Probably there is another state. So we are not solving it. This is called recursion. What we are doing is similar. So if you are able to handle this part, so what is the average waiting time? 1 upon lambda I we write, right? So if this whole is Mi, this whole is Mi, ith state, I to K. What is Mi? Let me write. Mi is the expected time it will take. So we are interested here actually. This one is Mi, that is a notation. So if this one is Mi, this one will be Mj. Now we'll try to connect these two, and then when you solve a problem, time and again you apply, then you will be able to solve. That is called recursion. So what is that exact formula? Let me write here. Mi will be equal to, I'll write here, my Mi will be equal to, let me change this. Probably we'll go with this. My Mi will be equal to, is it? No, it's not. My Mi is equal to, the time. First of all, my average waiting time, because waiting time follows exponential distribution, the parameter lambda, plus. If I leave I, what is the probability that I will go to J? Okay. Here there are so many chances. Suppose it's J, but J should not be equal to I, first state, and it should not be equal to K also, the last state. So this probability I will write, then I will write Mj once again. And this probability, whatever probability will write, this will be, if you remember, we don't have space. Mu ij, I will increase it. Awesome. Now this will be, this is so important. Okay, in terms of exam, this will be my mu ij divided by lambda I. Okay, that I explained. These are the Pij's. So this is the formula. This formula is very important. As I already mentioned you, this formula you need to remember. And if you feel it's complicated, I'll do something for that. So what I can do is I can take this, a bit logical, but it's easy, right? Subject is easy, not a problem. So you spend time, you do it.